In the previous video, I told you what the P equals NP problem is, and turns out it is unsolved. Nobody's figured it out. And so in this video, let's talk a little bit about why it's an open problem and what it would mean if the answer were yes. So there is a poll that's been done a couple of times of computer science theorists asking, do you think that P equals NP? That is, can efficiently verifiable problems also be solved efficiently? So of those responding, 83% said that they are not the same, 9% said they are the same, and 9% had other answers, like for example, it is an undefined problem, or there's like whatever it might be. Okay. So why is opinion generally negative? Why is it 83% negative? Well, there's two main arguments that if you go and read through the poll. One of the biggest reasons is someone would have proved it by now. If it's so important, and we've been working on this since 1971, should have been done. Another reason, though, is a little more philosophical. It says that creating the solution to a problem, it should be more difficult than verification. It shouldn't be the same amount of effort to verify as it is to solve. Now, to focus back on that first point, the idea that someone would have proved it by now, our own Dick Karp here at Berkeley, the quote he had in this poll was, "The only supporting arguments I can offer are the failure of all efforts to place specific NP-complete problems in P by constructing polynomial time algorithms." So what is that? What's this all about? Well, I'll give you a little bit of a flavor of this here. So it turns out there are lots of NP problems that all reduce to each other. So for example, as I said, all NP problems reduce to 3-sat, but 3-sat also reduces back to independent set, to the Hamiltonian path problem, the Hamiltonian cycle problem, and so forth. And this is well beyond the scope of the class, but it's a classic work starting actually with Dick Karp back in the 70s. So these problems are all known as NP-complete, and there are tens of thousands of them, and none have been solved. And what's interesting about it is because they all reduce to each other, that means that solving any of them means that you've solved all of them. So if you find a Hamiltonian path solution, you've actually just cracked open all these other problems out there. So I should note, just because it's on the slide, there are some problems which we know that they are in NP, but they have not been shown to be NP-complete. So for example, trying to factor a number into, or if you try to ask the question, does a number have exactly two factors that are both prime? That is a problem which is NP. You can check the answer quickly. But if you had an answer to that problem, we don't know how to use that to solve 3-sat. Okay, that's kind of a subtle point, but figured I'd mention it on the slide briefly. Now here's a really surprising fact, another one, which is that mathematical proofs are in the class NP. So I'll give you an example of an NP problem. I could ask, is there a proof that the Riemann hypothesis is true? So if the answer is yes, a yes answer could be easily verified. If you give me a proof and say, this is a proof of the Riemann hypothesis, I just need to check the proof. So in other words, if P equals NP, then in some sense, mathematical proof can be automated. So and another way of putting it is that if P equals NP, it means that checking a proof is roughly as easy as creating the proof. And this was actually first observed by one of the granddaddies of logic and thinking about all this kind of crazy stuff, Kurt Gödel, and you can go read about him if you'd like on the internet. But the quote translated into modern language is that an efficient procedure for what we now call NP-complete problems would have consequences of the greatest magnitude. Such a procedure would indicate that despite the unsolvability of the Entscheidungsproblem, which I will not describe, the mental effort of the mathematician in the case of yes or no questions could be completely replaced by machines. So what's fun about this is because mathematical proof could be automated if P equals NP, that is, if you prove that, and there's a little bit more detail here. I should be a little more careful. If P equals NP and we actually have a solution, we prove not only that they are the same, but we can also solve the NP problems quickly, then that means we can solve whatever math problem out there. So for example, in 2000, the Clay Mathematics Institute set up $1 million prizes for 7 different problems: the Hodge conjecture, the Poincare conjecture, the Riemann hypothesis, and more. And the last on this list is P equals NP. So this one's a little bit different than the others, because if it's true, then the proof that you constructed, if it actually gives you an algorithm that efficiently solves these NP problems, it will also trivially, I mean, trivial here is a bit of a moving concept. But if it's true and you have an NP solver that's very fast, because mathematical proof is itself an NP problem, you could trivially solve all the others, so you get $6 million for the price of $1 million. So now going all the way back to our earlier quest. Since space-time bounded compression can be reduced to 3-sat or longest path or independent set or any of these other NP-complete problems, then an efficient solution to any of them would basically act as a compression algorithm. So I could, because I can transform this into one of these problems, I could do the compression that I'd like. Okay. Now, what's so interesting to me about this? All right, well, this is going to bring together the title of this video. So this is Scott Aaronson. He's a very famous complexity theorist. He runs a blog, pretty cool stuff. And if you want to read more about NP completeness, I would recommend this document. It might be a little technical for you, but I think it's mostly readable. So he has a really great quote, which is, "I've heard it said with a straight face that a proof of P equals NP would be important because it would let airlines schedule their flights better or shipping companies pack more boxes in their trucks because they'd be able to basically do these logistical combinatorial problems very efficiently." He goes on to say that if P equals NP, then we could quickly find the smallest Boolean circuits, which is something kind of like a program, that output a table of historical stock market data or the human genome. It seems entirely conceivable that by analyzing these circuits, we could make an easy fortune on Wall Street, retrace evolution, etc. Broadly speaking, he says, if we can compress something, we can understand it, and that which we can understand, we can predict. So if we could solve the general case, if knowing something was tantamount to knowing the shortest efficient description of it, being able to compress it, then we would be almost like gods. I'll give you some diagrams in a moment to kind of elucidate what he's saying. Assuming that P is not equal to NP is the belief that such power will be forever beyond our reach. So, pretty cool. Okay. Now, there are those who have said out there, and perhaps rightfully so, that this is a little dramatic, but Scott Aaronson is generally a pretty above-board guy, very respected. He's the complexity theorist, not me, and so I figured I'd bring this to you because I found it quite fascinating when I first read this some time ago. All right. So in the next video, we're going to wrap up and kind of pick apart Scott Aaronson's conjectures a little, and that'll be it for today.